So the topic I'll be presenting on is mirrors, and this picture is from a scene in Inception. And if you've seen it, she, through the use of mirrors, she like puts them across each other, and considering they keep on reflecting each other, it makes it seem like it's endless, which like creates this like train station from her past look to it. So there are three different types of mirrors: flat mirrors, concave mirrors, and convex mirrors. Flat mirrors are usually the most common types of mirrors seen. Hence its name, it's just a flat mirror, and it will reflect an image the same size back at you. A concave mirror, it has the shape of a segment of a sphere where when looking at it, the center bends outwards. Sounds a bit confusing, but it's simply just like if you're looking at a spoon, which is a great example of concave versus convex. The concave part would be the inside of the spoon, and when you look at it, you can see like usually an upside down image of you. And then the convex mirror is the opposite of the concave, the same sphere type thing, where it's like the opposite side of the spoon. And when you look at it, you just see the same image looking back at you and upright, but it's a smaller image. So flat mirrors just shows like a flat mirror with just like the teapot. You can see like the same size image coming back at it. And here, the flat mirror, this is the object, and this is the mirror. It's kind of reflecting back at it, and it just shows like the image that's being created is right here, and why it's the same size is because distance p will be the same distance as q. Better elaboration of this would be this slide right here, where you can see the theta that's being reflected back at it. So this will be your eyes, and this will be the object. The theta that's being reflected back at it is the same here as here, and it's going to be also the same here as here. And that's why by height, since the height is the same, it's going to be the same. And also this distance, so p from the distance from q, as well as the p on the opposite side, will be the same distance from q. And once again, showing it's going to be the same it's going to be the same in like same sized image. And why? And since it's flat, it reflects, like it bounces off right perfectly without like distorting it. Okay, and then this is a real image. Is a light actually passes through the image point. And the only the examples of that we'll be showing it later though is a concave mirror when the object is placed outside the focal length. In a virtual image, light doesn't pass through the image point but appears to come from there. And those are like flat mirrors are always like that. Convex mirrors and concave mirrors when the image is placed inside the focal length. So a better elaboration on that from flat mirrors, it shows that this is a virtual image because the image that's being seen is on the other side of the mirror. Instead of like that side would show that it's virtual and not real. Okay, so and now so flat mirrors, just a quick explanation of them again, is the image is as far behind the mirror as the object is in front, since y, it would be the same size. And the image is unmagnified, which means same size, virtual, and it is upright. All right, and interesting use of the flat mirrors is here. You have this, most rear view mirrors of a car would have this, and it's called a day setting and a night setting. And so this would be like a wedge of the rear view mirror, and it's positioned in a way where this light that's hitting the rear view mirror, the bright part of it will hit your eye during the day when it's positioned like this during the day setting, and the dim part will go away, which is so you'd want that during like a day part where you could actually see it's all light outside, so you could actually see the car behind you with its lights. And then the night setting, so the light of the car doesn't like blind you because it would be so much brighter than because it's dark outside. It'll have the light would be positioned away where the brighter part of the light would only go out that way, and the dimmer part will only go only the dimmer part will go towards your eye. Okay, now on the next type of mirror, concave mirror, and this is shown like the example with the spoon. When you look at the spoon on the inside part, you'll see your image as they're inverted, blurry and smaller. Okay, so whenever reflected light actually passes through a point, the image formed there is real. So the concave is one of the confusing type things because there's like two aspects of it. But just to explain it explain what happens with the concave mirror, the way it's reflected. So the C right here, the center of curvature, which is this whole thing, the C would simply mean, say if this had continued going all the way, the C would be like the center of like that circle part, the sphere part, where the radius there is equal to the same as there, over here. All right, and then the principal axis is simply from C to B right here. All right, and now the way it reflects, as you can see here, the image reflects, bounces off there, image reflects and bounces off there, and the image is created right there, which shows that it's a real image considering it's created up front, up here, and not an image that's created back here. And yeah, so, but what would, like, I'll explain the next slide, what would happen if the object is in front of the C, or the center of the curvature, which would not be able to create that real image. And so I'll explain right here, and one more time just to show why it would create that inverted type of thing on when the object is placed behind this center. So as you can see, ray 1 reflects there, ray 2 reflects here, and now ray 3 reflects there. The point, the image part where they all hit each other is down here, which is below the principal axis, which will show why it's like inverted. And yeah, so the object's here and reflects all here, and this is what image created. Once again, real because it's in front and not behind. Now here, the object is placed in front of the center, which will make them all reflect in a way where they will not hit each other out here, well, they not will hit that part, that image right here, but instead we'll have to show the image virtually over here. So virtual, not real. All right, now convex mirrors, like we just explained, the outside part of the thing where you'll see your image as well, probably more magnified, upright, but as well as before, it'll be a smaller image. Okay, so like we just said, upright, virtual, smaller than the object. As it hits, so the object is here, and they all reflect back in that kind of way. The object will reflect outwards, and the image that's being created is from, so the center of the curvature, as we explained before, would, as if that line would go straight towards the object through the mirror right here, and then where it would hit, that part that's being reflected, make it go straight back to the principal axis part, and wherever these two lines now hit each other, that's where the image is being created. And as you can see, this part right here, so Q, is much less than P, which will show why the image becomes less in size. And as we'll explain later, but I'll just say right now, when the object goes further back, the image becomes smaller and smaller. And I'll explain that more fully later. All right, and so convex mirrors, the last part, this shows what we were talking about before with the candle. You can see that the candle will be a smaller image before. And so ray 1, ray 2, and ray 3. And you can see that center part being reflected, and that part that's being reflected is also, you can see that line coming out, that line coming out. And so this part where they hit, all these images hit each other, will be right, will show where they, like why it's virtual because it's behind, and where you'll see the image. All right, and then so like cool, like the uses of convex mirrors. So let's just explain that. Since convex mirrors show an image that is upright, clear, and reduces the size, these types of mirrors are quite common and useful for an instance like a store, so that the employees can watch the entire store and more easily keep an eye out for shoplifters. So you'll see this, probably seen this before, but when you walk into like a store, you can see like usually in a corner, like a convex type of mirror that you'll see through that thing. You can sense the whole like image from that thing is like less now. You can see like a broader perspective of it. So you can see the whole store and more like easily see what's going on. And another obviously common use is the side view mirror in a car. Everyone always knows where it says like on the bottom, like in black, objects in mirror are closer than they appear. And this, through that mirror, the driver can see like a greater amount behind him. So he doesn't, so he like, usually like could be much bigger blind spot if that didn't exist. Okay, and to further explain why the image for like a concave and a convex when you move the object will become smaller or bigger. First explain with the concaves. Sorry, easier. So say if the object is right here, that's where the object is. And we'll draw that line straight to the C, and then that one line being parallel to the center vertex thing. And then the way it would reflect would be around like that. So this is where the image would be. But say if we move that object just to the right, so closer to the mirror though, this part will still be the same, but that part going to the C will now be closer. So the new image would be around here, showing that will be a bigger image considering now it's like the virtual image will be closer to the mirror than before. And also one more interesting thing about all this, let me just erase these parts, and I'll show you again how that would look like this. That's where the original image was. Is show that, say if we have now the object being placed right here, that part that's being reflected back, so that part they used to have right here, would be the same right here, and the same would be the part, so that image you can see would be the same as where the object was placed, and now you can see this would just be like a flat mirror. So it shows like the similarities, like differences between like the concave and the flat mirror if you place it like directly at it right there. So now for convex, to explain this, you'd have your C around here, and then say your object is right here. I'll explain the rays in red. Let me just make this completely somewhere around like that. So the way it would reflect if it went straight would be around there, and say if it went reflected right back at it from here, it'd be around like that. And then if it reflected right back at itself, apologize, go through that line right there. There we go. And so that's where the image would be. But say if you move it so to show that when it becomes closer, the image becomes actually smaller rather than becomes farther. And when it becomes farther, the image actually becomes bigger. It shows that because, say if we move it to the right here, the object's right there, this part would obviously still be the same. But the part that would change, this would now become higher up here as it reflects back. And then the image that's reflecting right back off the mirror would be right there. So it would be right, now the image would be there. And as you can see, now that you can see that that part is like closer, that image being, so the image that the real image that you see off that mirror is actually like, so the reflection part you see is actually farther away, which shows that the image is actually becoming, the image is actually becoming smaller, rather than when it was back here, the image was actually bigger because the image that you saw right here is actually closer than that image that you see right here. All right, and that will be all my presentation for mirrors. Hope you learned something, enjoyed it. Thank you very much.